Geometric transformation and resampling. How we change raster coordinate systems, or give coordinate systems to rasters that don't have them. So just recall again that every raster layer, whether it is in a real-world coordinate system or just found on the internet, all have an internal column and row coordinate system. So we have columns across the top, and of course rows from east to west. Now, the coordinate system of a raster layer starts at 0, 0. And that's the top leftmost cell. So every raster has a coordinate system where the top leftmost cell is coordinate 0, 0, and that's for the internal raster coordinate system itself. If it is already in a GIS system and has a coordinate system assigned, you won't see 0, 0 up in that corner. In that case, you will find 0, 0 somewhere, either at the bottom left corner or somewhere else in geographic space, wherever 0, 0 is on the Cartesian plane that we see here, the X and Y axes. When we bring a raster image into ArcGIS Pro that does not have a real-world coordinate system associated with it, then it will orient that raster at 0, 0 in the real-world coordinate system that is currently being displayed in the ArcGIS Pro map window. So let's keep those things in mind. When we have no coordinate system for a raster, we will have to work with the internal raster coordinates, where row column 0, 0 is in the top left corner of the raster itself. Here are the rules for rasters to be used in analysis together. Every raster must be square, or rectangular, and oriented in a north, south, east, west direction. And that is true for every cell within the raster as well. So here are some examples. We have something which is like this. It has a bad orientation, but the cells are orthogonal. That means that the boundaries between the two cells, or the sum of the angles, or the internal angles of each corner of the cell, are 45 degrees. In a second case here, we no longer have orthogonality for each of the cells. So some of the angles inside are not 45 degrees anymore for every corner of the cell. And that means cells don't meet at right angles. Likewise, here's another case where we have a rotated and skewed raster image. And again, we have bad orientation because the raster itself is not oriented north, south, east, west. And we have non-orthogonality within the cells. So the last one here is what we would call a good raster. A raster which is square rectangular, where we have 90-degree angles between the intersecting cell boundaries, 45-degree angles for each corner inside each cell, and the entire raster is oriented in a north, south, and west, east orientation. So all rasters must look like this last one here before they can be used in analysis. And it's not always easy to tell if your raster looks like this, because when you're zoomed to a very small scale, you will not see that the raster cells are not cardinally oriented and orthogonal. And so we have to undertake a process within this type of environment or this type of situation called resampling. And we'll look at that in a second. Geometric transformation then is when we take a raster that has no coordinate system and we orient it with its cells into the real world using a reference map that has a real world coordinate system. And there are two ways that that is done. Well, there's one way that we undertake applying a real world coordinate system to a raster that doesn't have one, and that's called warping. And the second way in which we undertake geometric transformations of rasters is using projection. Projection is used when we already have a raster in a coordinate system within the real world, and we just want to change the coordinate system of an existing raster. These use equations that are well known to transform from one coordinate system to another. Warping, on the other hand, is used when we have no coordinate system for our rasters. And when we have no coordinate system for a raster, we must assign one. And warping is undertaken for that. Warping is also what ArcGIS uses when you bring a raster in that has a real-world coordinate system and you want to display it with your existing data in a different coordinate system. ArcGIS will warp between one coordinate system and another. It won't project. So that's a different process. That's an exact transformation projection. Warping is a statistical transformation, as we'll see in some cases. So whenever a geometric transformation happens, these things take place. The raster itself is translated, rotated, scaled, and or sheared. It can be two of these things, one of these things, or a combination of all of these four things can take place in order to put a raster into a new coordinate system, whether it's from an existing coordinate system to another existing coordinate system, both being real-world coordinate systems, or from a raster column and row coordinate system into a real-world coordinate system. So we'll have a look at these. Now, those things that I just talked about, warping, projection, translation, rotation, etc., can be done using these tools in ArcGIS Pro. For example, there's a warp tool to undertake what is called georeferencing. There's a project tool to change coordinate systems that are already real-world coordinate systems. And there's even functions to flip, mirror, rotate, shift, translate, and rescale rasters. So let's look at translation. So here we have a raster in a coordinate system, X and Y. And to translate a raster just means moving it without changing any of its other properties in the real world. So notice here, all we did is move the raster somewhere else within that coordinate system. Everything else stays the exact same. And that's called a translation, geometric transformation. We can have translation plus rotation. So we translate and then rotate. And again, that's two geometric transformations that take place. And if we were to zoom in very close on this second raster, we would see the cells of it are no longer oriented north-south, east-west. You will see many rasters that look like this, right here. The look of that raster is rotated, but if you zoom in very close, sometimes If that's a raster that's already in a real-world coordinate system, it's fine because the cells are cardinally oriented and orthogonal. But the whole raster looks like it's rotated. And that's because when we have a raster in a real-world coordinate system that's been rotated, there's actually a whole bunch of other cells that are part of the raster just outside here. And these are all no data cells usually, and so we don't see them. But if you turn them on in the visibility aspect or in the legend, when you go to the appearance tab, you could actually see that it's a completely square or rectangular raster. That's if it already has a real world coordinate system. So we have translation and rotation. And just because you see a rotated looking raster, it does not mean that it is in fact in need of any geometric transformation at all. You have to look closely at the pixels to see whether that's true or not. Here's translation, rotation, and scale. So we have the translation, rotation, and then a rescaling of that, in this case making it smaller. Finally, translation, rotation, scale, and shear. So shear just changes the makes a movement in this direction and that direction, but keeps all the parallel cell lines or divisions, they remain parallel during a shear operation. So these 1, 2, 3, 4 geometric transformations can take place together to provide a raster, a georeferenced coordinate system in the real world. Now, after that transformation takes place, so the geometric transformation, we will end up all the time with cells that are no longer orthogonal to each other, except for just pure rotation. But generally, again, whenever we're doing this, we have a combination of them, and we end up with cells that are non-orthogonal. And so they don't follow the rule of a raster in that every raster must be square, rectangular, oriented north, south, east, west, with the same holding true for the cells. So we would say it has a bad orientation and lacks orthogonality once we undertake a geometric transformation. And so what we have to do is create a new raster that covers the bad raster that's poorly oriented, non-orthogonal, and then we transfer the values from the bad raster to the new raster that is perfectly cardinally oriented and orthogonal. And that's called resampling, that process. So resampling takes cell values from a bad raster and puts them into a new good raster that is ready for analysis. Resample is also the function that can be used to change the scale of a raster. And usually either the scale or the cell size of a raster, resample can be used by itself to change cell size. So let's look at an example of resampling. This is called nearest neighbor resampling. So here I have a raster, and we're just concerned with this one cell. So this raster has nothing in it except for a categorical cell with a value green. So if I project that using any projection equation, for example, then my output raster would be a bad raster, no longer orthogonal, no longer oriented north, south, east, west, and it looks quite warped. So what we do in resampling then is we have to put a new raster layer over top of the old one. And this new raster layer is orthogonal within the new coordinate system that we projected to. Then we transfer that green cell value to the nearest neighboring red cell, and that's called a nearest neighbor resample, like so. So within our new space, in our new raster, we have the red cell being shifted a little bit in most cases, like that. And so that adds more positional uncertainty to whatever you're going to do with it afterwards. So remember, we already have positional uncertainty due to raster representation. Once we project or warp a raster and then resample it, we end up with more uncertainty because the actual cell for a object like this, which is a discrete object or categorical object, that cell can now change where it really originally was in space, somewhat. Well, again, just using a full raster. So here's a full raster that has 1, 2, 3 categories in its native coordinate system, or it's orthogonal. And then if we project that or warp it to a new coordinate system, then it looks like this. Again, we have a bad raster now, no longer orthogonal in any way. So we have to overlay a orthogonal raster in that new space on top of this warped raster, like so, and then transfer the values using nearest neighbor methods. That means whatever is closest to the new cell center, so in this case here, the orange will be closest to that new cell center, so that's nearest neighbor. In this case here, the closest thing again will be orange, closest will be orange. In this case here, closest would be purple. So purple will go there, purple will go here, purple down here, and then here, well, that's a tough one. We'll have to see if that's green or purple. And that's how nearest neighbor works. We just look for the nearest neighboring cell, and its attribute category is transferred to the cell value for the new raster. And the end product here looks like that. So it looks a little bit different than the original. And so we have, again, that uncertainty or error being put in because of resampling. So that's another bit of uncertainty to add up to anything else that you do. This is another diagram or way of looking at resampling. Here we have our warped grid, which is the black dotted lines. And the cells centers are marked in black. And then over top of that bad raster, which is in the black dotted lines, we put our new red one. And then we look at each cell. So here's the first cell center. And we see, okay, which of the other cells surrounding that, which cell center is closest? And that's just showing that here, that, okay, that cell center was closest. So whatever the attribute is of that cell center will be transferred to this new cell center here. So it's an alternative way of viewing the resampling process. Here is a third way of viewing the nearest neighboring resampling process. This here on the left is our input raster, the raster that has been or will be warped into the real world. On the right-hand side here, that's our new raster that was overlaid in the new space in the real world. And so we need to find a value for this cell here. And so we find out where that cell center is in the old coordinate system, and we find the nearest neighboring one right there. And so the nearest neighboring one to the new cell center is that value for this. And so that's assigned here and goes back over here. So it's another way to look at it. Same thing, 3 ways to look at the same thing. And it's very important to know and remember that nearest neighbor resampling is one of the only methods that is appropriate for categorical rasters. Some software may have other ones available. If there's a majority, for example, that could be used. So you may say, okay, take the majority of the surrounding 4 cells or something like that. But ArcGIS Pro doesn't have that capacity for resampling, just nearest neighbor, and that's for categorical data. So there are different resampling methods for categorical and continuous. For example, as I mentioned, for categorical data, nearest neighbor and majority are 2 possible ones. For continuous data, there are 2 choices: bilinear interpolation and cubic convolution. Bilinear interpolation uses the 4 closest cells from the bad raster to estimate the value of the new raster. We'll see that in a second. I'll explain it in more detail. Cubic convolution uses the 16 surrounding old cells, or badly oriented cells, to determine a value for the new cell center. Bilinear interpolation is appropriate for continuous data, as you can see here. Cubic convolution is also appropriate for continuous data, but it's a very special case that you should never use unless you have a reason to use it. And that's because cubic convolution can end up extrapolating values above or below the 16 surrounding or the 4 surrounding values. So you could end up with a higher value or a lower value than you might want. But it's very good for visualization. And in fact, you could use, if you're just interested in using resampling to better visualize a raster layer, you could also use categorical data with cubic convolution. But again, only for visualization purposes, never for analysis. For analysis, you're going to be using nearest neighbor for categorical or bilinear for continuous data. So here's the example of bilinear interpolation. We have, again, our original raster right here. And then we have a output raster in our new coordinate system, and its cell center right here. So for that cell center, we find where it is in the old coordinate system. And then the 4, 1, 2, 3, 4 surrounding cell centers are examined. And depending on how far our new location is from those 4 old cell centers, a new value here is determined. And that value will never be below or above any of the surrounding values there, because it creates what's a 2-dimensional plane and then finds the location on it. It's a distance-weighted average. And so it's very appropriate for continuous data, because continuous data theoretically continuously vary. And so this type of resampling follows that assumption. And here's the cubic convolution example. The difference here is that there's our new cardinally oriented cell. We find where that cell would fall within the original raster coordinate system. And then these 16 surrounding cells are used to create a spline surface. And that's a contorted and can be highly varying surface depending on the surrounding values. And so P could be different from the surrounding 4 values, for example, depending on what the values were. And so it's not really appropriate for analytical purposes because of the fact that it can lead to values that are higher or lower than the surrounding cells within that raster. But it's very good for display purposes and is highly recommended that anytime you need a raster for display purposes, that you use bicubic or cubic convolution. Convolution is just another name for filtering in raster. So a cubic convolution or bicubic or just cubic, 3 names for the same type of thing.